So let's go over two homework problems involving integral of spherical coordinates. So this is the first one. Over the solid K defined like this: x squared plus y squared is plus y squared plus z squared is equal to 9, and z non-negative, which is a solid hemisphere centered at origin radius 3. So the picture will be something like this. Solid hemisphere centered at the origin radius 3. It was about to calculate the integral triple integral over k of x plus y plus z dv. Okay, so for this problem, one of the idea was to ask you to use the symmetries of the problem and to simplify from the start this integral. Because the nature of this domain, the triple integrals of x and y over the domain are by symmetry 0. So this integral reduces to triple integral over k of z dv by symmetries of the problem. It's obvious, right? So if you look at this hemisphere divided into two pieces, you look at the part of the solid hemisphere corresponding to x bigger than or equal to 0. On that part, half of the hemisphere, the function x is positive, and on the other part of the hemisphere corresponding to x is negative. On the other side, right, on the back, x is negative, and those two parts balance, two integrals balance each other. So the integral of x over the part of the hemisphere corresponding to x bigger than or equal to 0 balances the integral of x of the part of the hemisphere corresponding to x negative, giving the triple integral of x over the total hemisphere 0. Same goes for y. So that's why we discussed about this many times. This triple integral reduces to triple integral over k z dv. And now we can use a standard spherical coordinate. That will be triple over k rho cos phi, also known as z, times dv is rho squared sine phi d rho d phi d theta, also known as dv in spherical coordinates. And this hemisphere is actually a box in spherical coordinates, so we can really represent it as rho is between 0 and 3. Phi is from 0 to pi over 2 because of hemisphere, and theta because of the rotational symmetry of the hemisphere around the z-axis, theta is from 0 to 2 pi. So that means the hemisphere is a box in spherical coordinates. Then, integrating a separable function over a box by using SOR principle will yield the triple integral is the product of three simple integrals. The rho integral is integral from 0 to 3. Let's see, rho squared, rho cubed, d rho. Integral, the t integral from 0 to pi over 2 is the range of phi. Sine phi cos phi d phi. And finally, the theta integral, we only have a d theta here. Integral from 0 to 2 pi d theta. And let's see, this will be rho to the power 4 over 4 from 0 to 3 is 81 over 4. The second one is, well, look at the function sine phi cos phi, and antiderivative will be 1/2 sine squared phi from 0 to pi over 2. That will be 1/2 And the last one will be 2 pi. So the result will be 81 over 4 times 1 half times 2 pi, and the final result of this problem is 81 pi over 4. 81 pi over 4. There goes the first homework problem, exercise 1. Now let's discuss the second problem, exercise 2. Exercise 2 involves the integral of a product over a solid, full solid sphere, not really sphere. So in exercise 2, K was the following: x squared plus y squared plus z squared less than or equal to 1. So it's a unit sphere in 3D. Center the origin radius 1. Unit sphere in 3D. So that means rho is from 0 to 1, p is from 0 to pi, and theta from 0 to pi. This k in spherical coordinates. Over this domain, the problem was the following. So calculate the triple integral over k of x squared, y squared, z squared, dv. Why I gave this problem? Because previously it was discussed that if we still use a product but x, y, z dv, so noted, by symmetry reasons, triple over k of x, y, z dv equal to 0, and I told you to explain that, which is very similar to what we discussed in the previous problem. But this subject is not 0. So let's calculate triple integral over the unit sphere of x squared y squared z squared dv. Okay. So let's start. Okay, this is I mean, this is to remember, is the standard stuff of the standard spherical representation of the unit sphere, and let's call this I, and let's start. I will be triple integral over k of the following: x squared, rho squared, sine squared phi, cos squared theta. That's x squared. Y squared, rho squared, sine squared phi, sine squared theta. That's y squared. So this will be x squared, y squared. Z squared is rho squared, cos squared phi, is z squared. And then we have to put dv, rho squared, sine phi, 0, dphi, d theta, also known as dv. And now equals to, so let's try to group together like terms here. So triple over k of rho squared here, another rho squared, another rho squared, another rho squared, rho to the power 8. What about phi? Sine squared phi, another sine squared phi, another sine phi. So the sine phi is sine to the power 5 phi. Let's see, we have another cos squared phi. And we got rid of phis. What about theta? Sine squared theta, cos squared theta. And then 0, dphi, d theta. And that will be separable over rectangles, SOR. Integral from 0 to 1, rho to the power 8, 0. Integral from 0 to pi, sine the power 5 phi, cos square phi d phi. And then integral from 0 to 2 pi, sine square theta, cos square theta, d theta. So we got three integrals, let's call them I1, I2, I3. Let's calculate each one separately. Obviously, I1 is 1 over 9, so I need some space on this small chalkboard. So I'll erase. Now that I got the outcome, the temporary outcome is we are very close to finish. We have here. We need to calculate each integral separately. So let's do, so I1 equals to 1 over 9. Okay, let's do I2. I sub 2 is integral from 0 to pi sine the power 5 phi cos square phi d phi. And if you remember from trigonometric integrals, it's that type of integral where we have a odd power of sinus, and then we can, in that case, remember we separate the sinus, we do the substitution, cosine phi equals to u. So let me rewrite this as integral from 0 to pi sine the power 4 phi cos square phi sine phi d phi. So we just separate the signs. And then we use the substitution, cos phi equals to u. If the substitution is cos phi equals to u, let's write down on the spot the equality of differentials, minus sine phi d phi equals to du. Phi was from 0 to pi, 0 dot dot pi, and then u, which is cos phi, goes from cos 0 to cos pi, so 1 to minus 1. Let's see what we got now. So this integral transforms, converts into integral from 1 to minus 1. Sine the power 4 is the square of sine squared, is the square of 1 minus cos squared. So 1 minus u squared squared. So this would be 1 minus u squared squared. This will be a u squared. Sine phi d phi from here, this will be minus du. So let me convert everything. Here is u squared times 1 minus u squared squared times minus du. But we can use this minus from minus du as a price to convert the integral from minus 1 to 1. And then if I leave here du. So we got integral from minus 1 to 1, u squared times 1 minus u squared squared du. If we open the parentheses, we get integral from minus 1 to 1. That's u to the power 4 minus 2u squared plus 1. With the u squared in front of it will be u to the power 6 minus 2u to the power 4 plus u squared du. Okay, we don't need this anymore. That will be so that's an even function. So if we integrate an even function from minus 1 to 1, is 2 times the integral of that function from 0 to 1. So it's 2 times antiderivative is u to the power 7 over 7 minus 2u to the power 5 over 5 plus u to the power 3 over 3 from 0 to 1 equals to 2 times 1 over 7 minus 2 over 5 plus 1 over 3 which is 2 times. Okay, the common denominator here is 7 times 5 is 35 times 3, 105. So let me look at my notes. I calculate this one. So uh, 2 times 8 over 105, right? This integral. So this integral turns out to be 16 over 105. So I sub 2 equals to 16 or I sub 1 equals to 1 over 9. I sub 2 is 16 over 105. Let me write it here. I sub 2 equals to 16 over 105. Okay. Now let's do I sub 3. We got I sub 3 here. And the last integral is I sub 3. There was integral from 0 to pi. Sin squared is theta, cos squared negative theta. Now if we remember a easy trigonometry formula, double angle sine 2 theta, if you recall, equals to 2 sine theta cos theta. We can divide by 2 both sides. 1 over 2 sine 2 theta is sine theta cos theta. Therefore, we square both sides. 1 over 4 sine squared 2 theta equals to sine squared theta cos squared theta. And this formula for sine squared theta cos squared theta we use in this integral. So sine squared theta cos squared theta equals to 1 over 4 sine squared 2 theta. 1 over 4 is a constant. We take it in terms of the integral. 1 over 4 integral from 0 to pi of sine squared theta of sine squared 2 theta d theta. So 1 over 4 integral from 0 to pi sine squared 2 theta d theta. Let me get this stuff. And then we use again the formula of double angle. So that will be 1 over 4 integral from 0 to pi of 1 minus cosine of the double angle 4 theta divided by 2 d theta. And now this 1 over 2 again, we take it out of the integral as a constant, so which is 1 over 8 now here. And then no more over 2. Okay, so the integral difference of the integrals, integral of cosine of 4 theta is obviously 0 from 0 to pi. So this reduces to integral from 0 to pi of d theta, which will be 2 pi. So the result will be 1 over 8 times 2 pi, which will be pi over 4. So that's the value of I sub 3. So I sub 3 equals to pi over 4. So I sub 1 is 1 over 9, I sub 2 is 16 over 1 over 5, I sub 3 equals to pi over 4. So now then the answer to the problem will be the product, this product, the one more. We'll double check everything anyway. So so I will be I1, I2, I3, which will be 1 over 9 times 16 over 105 times pi over 4. Let's see what we can do here. 4 and 16, you can simplify 4 and 16, get a 4 here. 9 times 105, 945. So 4 pi over 945 is the answer to the problem. The triple integral over the solid unit sphere of x squared, y squared, z squared dv.